Okay, so good morning, everyone. This is our second class of the semester. I'm glad to see all of you today. It's very nice. I hope you're not dropping the class after this, hopefully. Okay, so today we're going to continue with our slides are from the previous week. Yeah, so last week, what did we learn? Anyone still remember? So we introduced you with the transport phenomena, the definition of the transport phenomena, right? So the transport phenomena is actually a phenomena that's actually where something's transporting. Okay, so in terms of chemical engineering, transport is includes three things. Okay, includes three things: mass, momentum, and energy. So in when we considering if there is a transport phenomena going on, we need to have measurable parameters for energy, mass, and momentum to define if there's any transportation going on, right? So of course there must be a gradient or difference in terms of the measurable parameters. In this case, it's temperature, concentration, and velocity, right? That represents energy, mass, and momentum transport respectively, okay? So if there's a difference in terms of these physical properties in different locations, then there will be a transport going on, okay? So if there is like, for example, a constant or equal temperature between two places, there won't be any energy transport because the two spots have the same property, okay? T1 and T2 are equal, so there won't be any energy transport. Same thing with the concentration or velocity, okay? And apart from that, I introduce you with the types of variables, right? That we have scalar, vector, and also tensor, okay? As well as the operator. So operator is also includes the scalar operator and also vector operator, okay? So you are familiar, I hope so, familiar with the dot, differential, what else? Divergence, del, is that right? So today we're going to go through all that. We're going to apply all that into the equations too, okay? So don't just forget about it, all right? Because we're going to apply all of those variables and operators in my part for the rest of 8 weeks, okay? The rest of the slides that I have left off since last week is the three types of transport phenomena. So, excuse me, I'm not quite recovered yet. You already understand what transport phenomena is, right? But today we're going to go into details of mass transport, momentum transport, and energy transport. Because in terms of transport, okay, there are two transport mechanisms, okay? So we're going to go through that in just a second, all right? So like you know that we have momentum transport, mass transport, and energy transport. There are actually two types of mechanisms in order for each one of these to be able to transport, okay? So the two mechanisms that I just mentioned is molecular transport and convective transport. So as the name being said, okay, molecular transport, we consider it as a molecule by molecule, okay? So if you compare or if you can consider, think of two molecules closing with each other, okay? And if they have different physical properties, in this case, it's temperature or mass or velocity, okay? So there will be a transport between molecules to molecules. I'm going to show you in the next slide later so that you can have a better picture and understanding, okay? And in terms of convective transport, in this case, we consider it as a whole or like a bulk transport. Okay, so let me compare between molecular transport and convective transport. So in terms of molecular transport, you can see it as like a very microscopic view, like molecule to molecules, like I just mentioned, right? But in terms of convective transport, you consider it as like a macroscopic, like a bulk solution or bulk fluid. Okay, that is flowing. Okay, so in this case, if you can compare molecular transport, you can consider that the medium is staying still, okay, is not moving. But for convective transport, the medium is actually moving or flowing. So in this case, if I simplify the definition between these two types of transport, molecular transport can occur in liquid, fluid, let's say liquid gas, that is staying still. That is staying still. And also solid, because solid, you know that molecules of solids are staying still, right? But in terms of convective transport, it can only occurs in fluid. So by I'm saying fluid, it means that it includes gas and also liquids, right? Because gas and liquids can flow or it can move. But in terms of solid, for example, this pointer here, the molecules of the solid here are fixed, right? It's not moving like liquid or gas. So in this case, solid convective transport cannot occur within solid. Okay, if you know what I mean. But I will show you in the next few slides so that you can have a better understanding of one of each. Okay, so you can see here that momentum transport, mass transport, energy transport, the mechanism that can transport, it can be either molecular transport or convective transport or both. Okay, same thing with mass and energy transport. So let me show you and explain to you about the molecular transport and convective transport in details. Okay, so let's start with the molecular transport again. So in these examples, you've seen this last week, right? So we have two parallel plates, and between these plates, we have a liquid, okay? So at time zero, everything is staying still. We're not pulling any plates, okay? So if you consider the molecules of liquid along the y-axis, 1, 2, 3, 4, 5 here. So the chunk of water, number 1 to 5 represents the let's say like a chunk of water in y-axis. Okay, so everything is staying still at this point. Okay, at this time. So at time more than zero, I start pulling the top plate. Okay, so of course the chunk of water or molecules 1 will start to move with the top plate with the same velocity. Okay, and it's going to drag the molecules number 2 and number 3 and number 4 and 5. Okay, so you can see here that there is a distribution of velocity now along the y-axis, because the velocity in number 1, the molecule number 1, is higher than that of number 2. Same thing, the velocity of number 2 is higher than that of 3, and then 4 to 5, and velocity of number 5 is equal to 0, because the bottom place is fixed, right? It's not moving. So the velocity here is 0, according to no slip condition that I just mentioned last week. All right. So you can see here that along the y-axis here, there is a gradient or a difference in velocity. Okay. So in terms of molecular transport, you can see here that there is a like a transport of velocity, okay, in molecules. From molecules 1 to 2, molecules 2 transfer to number 3, number 3 transport to number 4, and then number 5. So this is the example of the molecular transport that I mentioned, okay, because we consider it as like a molecule to molecule transport among molecules that is close to each other. All right, and you can see here that the medium is not moving. It's like it's fixed, okay, along the y-axis. All right, but in terms of the convective transport that I explained to you earlier, we consider it as a bulk. Okay, so if same example. Okay, we have a flowing fluid between these two parallel plates. So if I keep pulling the top plate at the velocity Vx here, so in terms of convective transport, if I consider the location x1 and x2 along the x-axis, okay? So I'm going to consider the system in a red box here, okay, as a bulk fluid. So we're going to consider it as a, oops, sorry, what's going on? As a convective transport, because the medium, so in this case it's the fluid, is moving, okay, it's flowing, so it's moving. So in this case it's going to convect the velocity from this point x1 to x2 in this case, okay? So these two mechanisms can be incorporated in mass and energy and momentum, like I mentioned, okay? So if we consider energy transport, of course, we're going to see if there is any difference in terms of temperature, okay? But in terms of mass transport, we're going to consider it as a concentration gradient, okay? And so the last one is the momentum transport. We're going to see if there is any gradient in terms of velocity. So of course, all of these variables always starts from goes from higher to lower. Okay, so for the momentum transport, I actually explained to you about it. Okay, so if it's a momentum transport, we're going to see if there is any gradient in terms of velocity. Okay, so if we consider the molecular transport, we're going to see if there is any gradient in velocity. Okay, between molecules to molecules, molecules to molecules. So in this case, for example, right here, you can see that molecules 1 and 2 have different velocity, right? So in this case, there is a molecular transport in terms of momentum, okay? And in terms of convective transport, so if you can consider or compare the location x1 and x2, so the fluid is carrying the momentum at x1 flowing to x2, okay? So of course there will be a momentum transport is in terms of convective transport. All right, so the way we look at molecular transport and convective transport is a little bit different, okay? Like I mentioned again, molecular transport, we can consider it the medium that is staying still, okay? But for convective transport, the medium must be flowing or moving, all right? So this is the example for momentum transport. Let's go to the next one, energy transport. This example will be more understanding, I think, in terms of energy transport. So as you know that energy transport have three different types of mechanisms of the energy transport, right? Conduction, convection, and radiation. But in our class, we're just gonna focus only on conduction and convection, okay? So conduction, of course, you know that when conduction occurs, it means that the system or the molecules must occur in solid, right? The medium is not moving, okay? So in this picture here, if I have the red side, the left-hand side, which is hotter at T hot, and on the right-hand side here, which is another solid, which is has lower temperature, T cold, okay? And putting them in contact with each other, okay? What's gonna happen is that, so if we apply heat, of course, the left-hand side, the temperature will be higher, okay? So the energy will be transported to the right-hand side because the temperature is lower, okay? So in this case, the conduction occurs. So in this case, conduction is the mechanism to transport energy, right? So it's actually a molecular transport in terms of energy, okay? Because these two solids here or two blocks here are solid and molecules of solids are closing with each other, right? Are close to one another. So you can, if I represent by this spheres right here, representing as molecules of solids. So you can see that the left-hand side one will have a higher temperature, so it's going to vibrate, right? So the higher temperature, the one with the higher temperature or higher energy, okay, is going to vibrate more, and then it's going to transfer its energy to the right hand side, which has a lower energy or lower temperature. Okay, so it's going to transfer the energy to the right hand side and keep doing that to the very right hand side there. So in this case is the molecular transport in terms of energy transport. Okay, so there's a name for energy transport, which is the conduction. Okay, but for convection, in this example right here, of course, there won't be a convection or convective transport because the medium is not moving, is not flowing, right? Because this is solid. So if I show you another example, oh, sorry, I have another graph show you. So if I plot, sorry, go back to this example again. If I plot the temperature with respect to the distance right here, you can see that there will be a temperature gradient along the distance on the x-axis, okay? So in this case is the molecular transport. All right, another example that I want you to explain to you about the convective transport. So if I have a hot plate on the ground like this, and I have a flow of fluid, okay, which is cold. Oh, it's a flow of cold water, okay? So in this case, do you think there will be a convection transport going on? Convection, of course, right? Because the medium, which is the cold water now, if we take cold water as a system, okay? Because if we take hot plate as a system, it won't be, it will be the other way around, right? We'll come back to this later. So if we consider cold water as a system, and right now our system is moving and is flowing now, okay? So of course there will be a convection going on. So in this case, you can see here that the cold water flow from left to right. On the left-hand side, it's still cold, right? The temperature is still low. It receives the heat from the hot plate at the bottom, okay, and moved or flow to the right hand side. So it carries the heat and flow under the convection to the right hand side. So of course there will be a convective transport in this case, but the way that the cold water receives heat comes from conduction. Okay, because if you take a look at this y-axis right here, so if we take a vertical line as a y-axis, the heat actually transferred in a vertical way, right? Going up. The heat is going up like this. So if you think that this is the molecules of cold water in y-axis. So the heat or the energy is going to transfer to this molecule, up to this molecule, to this molecule, and this molecule. So when there's a cold water flowing in, it receives heat, right? And it's flowing away and carry the heat along with it, all right? So in this case, there will be both molecular transport, which is this one, okay? Molecular transport, because the heat is transferred molecules by molecules. The medium is not moving, okay? So in this case, it's the molecular transport or conduction, okay? And also convection, that as a result of the moving of cold water, okay? You have a better understanding about the molecular and convective transport. Okay, but in this case, you can see here that even if we have both molecular transport and convective transport, in this case, the convective transport dominates conduction. Okay, because of course there's a flow of the cold water, so the convection will dominate the conduction in this case. So here you can see that not only we can have only one type of mechanism of transport, there can be both of them at the same time, and which one of that can dominate the other one. All right. And okay, this just popped up. And the last one is the mass transport. So same thing with the mass transport. We also have molecular transport and the convective transport. Let's take a look at this one first. So if we have a cup filled with water, for example, and I have a cube of sugar, for example, okay, and I leave it like this for a while, for half an hour or an hour, what do you think is going to happen? It's going to dissolve in water, right? And it becomes like a single phase of liquid, okay? So what's happening is that there's some transport of mass, in this case is the sugar, right, into water. And do you think in this case the medium, if we take water in the cup as a medium, as a system, the thing is moving? It's not moving, right? It's just staying still in the cup. So in this case, there is a molecular transport going on, okay, from higher concentration to lower concentration, okay. Higher concentration in this case is the chunk of the sugar itself, and then the lower concentration in this case is the water, okay. So of course, sugar will dissolve or diffuse into liquid phase and then become fully dissolved at the end. All right. So in this case, it's the molecular transport. And for mass transport, in terms of mass transport, molecular transport in terms of mass, we call it as a diffusion. Okay, diffusion. You will hear this term a lot. Okay. And the other one is the convective transport. So in this case, if I put the sugar, same thing, okay, into a cup of water, and now I stir it, okay, with a spoon. So now there's a movement going on, all right? So when we have a movement right here, the medium is actually moving now. So there is a convection going on, okay, convective transport going on. So in this case, it will be convective transport. All right. But do you think in this case there is a diffusion going on too? Yeah, there is. Okay. There is both convective transport and molecular transport or diffusion going on. But in this case, diffusion might not be as dominated as much as the convective transport. Okay. So you can see here that when we design, like for example, in terms of chemical engineering unit operations, for example, mixing tank, we should normally have like a propeller or impeller to stir it up, right? To induce the mixing, right? Not just like leaving it and let the solution to mix on its own by diffusion, because it's going to take forever. All right. So that's why transport phenomena is very important subject in chemical engineering. All right. So to summarize all the introduction of the transport phenomena, so you can see here that transport, even if it's mass, momentum, or energy, it can be transported by two mechanisms. Okay. It can be one or both. Okay, which is the molecular transport and convective transport. So the transport can varies with time, as you all know, right? So today we're going to start derive an equation of conservation, okay, for both, not both, for all mass, momentum, and energy. We're going to go through one by one. We're going to start with mass transport first, and then we're going to go through momentum, and then the last one will be energy. Okay, we're going to derive an equation, conservation equation for all three types of transport. That is going to describe the behavior of any types of problems or phenomena, any types of system. Okay, so like I said that any types of system, it can vary with time. So whatever we are deriving as an equation, we're going to convert it into in terms of the transport rate, because yeah, it's respect with time, okay? And of course, it depends on the area too. Like I said that in transport phenomena, we focus things very very specific, right? Like a microscopic view. So out of the whole system, we consider only a small piece, small area out of the whole area, right? So in this case, the transport rate that we're going to derive is going to depend on the area too. So we're going to transform the terms into the transport flux, okay, in terms of the, so it's going to be with respect with time, with not only time, but on the area too, all right? And then last, we're going to, at the end, we're going to have the momentum transfer flux, mass transfer flux, and energy transfer flux, which will be our final goal of my part, okay? So from this three terms right here, we're going to have, from this equation, we're going to get or derive or determine in terms of the velocity profile, concentration profile, and temperature profile at the end, okay? So that will be our summary of my part for the next 7 or 6 weeks, all right? So, all right, so right now I'm going to switch to writing now. So please excuse me that I won't be standing anymore because I'm going to write, all right? I have to stop sharing. And then, hold on. Okay, I think everyone in Zoom can also see, right? All right. In terms of transport phenomena, you know that we look at things microscopically, right? So if we have any types of system like this, okay, it can be any shape, all right, in any coordinate system, okay? So we're not going to take a look at the whole system, like a whole piece that I'm drawing right now, okay? But we can actually only consider a small piece, a small area like this, okay? Which represents the whole system, okay? So if we have this small piece, I'm going to make a shade here. So we're going to consider if there is any flux coming in and out, okay? Flux in this case is the transport flux that I just mentioned, okay? Because transport flux in this case is going to be either mass flux, right? Momentum flux or energy flux, okay? And also in terms of time as well. So we're going to consider in this small area here, if there is any flux coming in or out, okay? So if I have a normal vector n, okay? I have a normal vector n. So in this case, within this small area, there can be any flux coming in or out. So let's say if I have a velocity, okay, so velocity is a vector, right? So I have I underline a single line too, okay? So velocity can be in any angle with the normal vector n, okay? So if I want to find the volumetric flow rate. Volumetric flow rate. So it's going to be equal to velocity times cross-sectional area. Is that right? Okay. So in this case, it's going to be integrate of velocity cosine theta ds. So if I take s is sorry, oops, sorry. S is the area of the small area that I showed you, okay? So ds is going to be the small area here. And if I integrate with the v cosine theta ds, it's going to be equal to volumetric flow rate, right? But you know that velocity is a vector, right? Velocity is a vector. But volumetric flow rate, is it scalar or vector? Scalar, right? So it won't match. On the left hand side here, you see that it's volumetric flow rate, which is the scalar. But on the right hand side, which is velocity, is vector, right? So on the left hand side is scalar, on the right hand side is the vector. So we must transform the term in to be similar. Okay, so I have to change it into v dot n is normal vector, okay? So right now, we're going to have the right-hand side to be scalar now, okay? So vector dot vector is equal to scalar, as I already explained last week, right? So right now, both sides are equal and have the same type, which is the scalar, okay? So if I zoom in the small area ds right here, there could be any flux coming in and coming out. For example, it's coming out, right? So the flux that's coming out here can be in any sizes, okay? It can be small or big or, vary. So in this case, we have to integrate them. So like I show you here in this form to calculate the volumetric flow rate. We're going to integrate it so that it will be like at the end it will be the average of the volumetric flow rate. Okay, so right now we're going to define the direction of the small piece here. So whatever's coming out, I'm going to define it as a positive sign. Okay. And whatever's coming into the small area is going to be negative sign, okay? Because after this, we're going to start deriving the conservation equation now, okay? So we will set as the sign like this, so we have the same direction, okay? So in this system right here that I showed you, okay, there could be a transport going on, even if it's a mass, momentum, or energy, okay? Even if it's anything, if it can be a single transport or both of them or all of them, okay? But it must follow the conservation law, okay, or the conservation rule, which is in minus out plus generation term equal to accumulation term. You all know this equation, right? So everything must follow this equation, okay? So right now, I'm going to show you here that even if it's mass, momentum, or energy, we're going that's coming in or out of this system, okay? Or we define ds right here. We're going to focus only on the ds right here, okay? We're going to consider if there is any in term, out term, generation term, and accumulation term that is occurring on this small area ds here, okay? So as I showed you previously, that any types of transport must be with respect with time, right? It can change with time. So before I move on to deriving the conservation equation right here, we are going to understand about time derivative first, because there are three different types of time derivatives that is going to be involved in this conservation equation, okay? So in terms of the time derivatives, okay, there are three types. The first one is partial derivative. Okay, so it's the, let's say we use concentration, so it's going to be in terms of this, okay? Let me show you the example so that the example so you can understand better. So if we standing by the river, okay, for example, and there is an observer right here standing by the in the river, okay. So there's a flow of liquid, right? A flow of water in the river, okay? And if I drop food coloring, for example, okay? So the food coloring right here, what's going to happen to this drop of food coloring? It's going to, I can hear the word diffuse, right? What else? And move along with the flow of water, right? So if I set a coordination system for this, let's say it's let's make it simple as a Cartesian coordinate. This is x and y is going into the screen, okay? So the partial derivative is actually meaning that the observer is observing the food coloring, a drop of food coloring right here, okay? And the position of the observer is fixed, okay? So he is not moving, okay? And he's going to see a variation in concentration with time, okay? So right here, dc by dt, I can say that x, y, z are equal are constant. It means that the position of the observer at x, y, z is constant. So he's not moving. So he can just see the concentration change with time. So if I plot what he's observing, okay, with time, T and C, okay? T and C. So what he's observing can be something like this, okay? Like the concentration starts to increase and then disappearing, okay? But if we have the other person or another observer, okay, standing right here, which is a different location, okay? So it will be in a dc by dt x1, y1, z1, which is a different position of the other guy. All right. So the concentration change with time that he can see can be something like this. Okay. So what I'm saying is that in partial derivative, the concentration is changing with time only, where the observer is fixed. Okay, he's not moving. Okay, so the plot of the of different observers will be different. Okay. The other one is total derivative. Total derivative, which is dc by dt. Okay, so in this case, it will be a different case. So in this case, if we have right now, if we have a boat, okay, a motorboat, and the observer is actually standing in the motorboat, and he's moving with a different velocity with the velocity of the flow of liquid in the river. Okay, so he is moving too. So in this case, it's going to be a total derivative where dc by dt is equal to partial derivative concentration with time. Okay. So you can see here that what he's observing is that the concentration of food coloring will be changed with time, okay? And it will be changed with the position too, in X direction, in Y direction, and in Z direction, okay? And if you see this term right here, dx by dt, dy by dt, and dz by dt is actually a change of location of the observer with time because he's moving at different speed with the speed of the flow of liquid in the river. Okay, so dx by dt is actually a change of position in x direction with time, y direction, and z direction. Okay, so observer is moving at different speed with the flow of fluid. Okay, so of course, what he's seeing in terms of the concentration change, okay, will be different to the previous one, which is the partial derivative, because he's now moving too at different speed. Okay, all right. Any questions about this? All right, and last one is substantial derivative, which is capital D, yeah, dt. Everything looks similar, right? Everything is dc by dt, okay? Right now, for substantial derivative, it's going to be different, okay? The observer is no longer on the motorboat, okay? But right now, he's on a raft. Let's say this is a raft, okay? So a raft meaning that he's moving with the same speed of the flow of fluid, okay? So this is the flow of fluid, right? He's moving along at the same speed too, okay? So the concentration change with time that he can see is going to be in terms of substantial derivative now, okay? dc by dt equal to, let me write first and I'll explain later. All right. So yeah, the observer is on a raft now with the same speed, moving with the same speed of the flow of water. Okay, so what he's seeing, the change in concentration of the food coloring will be changing with time, of course, and it will be changed with the position in x direction, in y direction, and also in z direction too. And vx, vy, and vz that you're seeing in the equation is actually the fluid velocity, okay? Vx, Vy, and Vc is actually the velocity of the fluid, okay? to rewrite this equation, okay, to make it to make it short, let me show you right here. Circle this term here. You can see here that what I'm circling right now is actually a summation of the Vx dc by dx plus Vy dc by dy and Vz dc by dz, okay? Is actually equal to V dot del C. This thing comes back again. Can you go back to the previous slide from last week? We already went through this term all together in the class, remember? Okay, so V is actually the vector. So last week it can be equivalent to vector A, for example, okay? And del C is actually equivalent to the del phi, because C is scalar. Phi that we mentioned last time is also scalar, right? So the whole term here is equal to V dot del C. Okay, so please go back, review the lecture from last week. So you see that the summation, or I mean the product of this term here can be distributed into this term. Okay, so right now I can write that dc by dt, or substantial derivative of concentration, is actually equal to dc by dt plus v dot del c. All right. Any questions about this? So now I think you can understand and differentiate among these time derivatives, okay? We have partial derivative, total derivative, and substantial derivatives, okay? They all have different definitions, okay? And when we apply it, it depends on the circumstances as well, okay? The which one? Substantial derivative, V dot del C. So if you go back to the previous slide last week, yeah, you will see that it can be distributed into this term. So you can take V vector velocity here as a vector A, okay? Last week, remember? And C is equivalent to phi, because phi and C are scalar, right? Yeah, same thing. Please go review the lecture last week, all right? Any questions from Zoom? No, all right. All right, so now let's go back to our deriving the conservation equation now, okay? So more fun stuff is coming your way. Okay. We're going to start deriving the equation of conservation, because we're going to apply this equation in all types of transport, which is mass transport, momentum transport, and energy transport. If you if you have taken transport phenomena in your undergraduate course before, you might have remembered that when we solve the equation back then, we do the shell balance, right? For example, like we have a pipe system like this, right? Flow of fluid. And the way we do that is to cut into a small shell like this. And we're going to consider, right, what is coming in and out of this shell, right? And then we're going to construct of each term in minus out plus generation and equal to consumption. It's accumulation, right? But in our graduate course here, okay, we're not going to do the shell balance approach anymore, okay? We're going to do the conservation equation, which will be different because it can be applied to all types of transport, including mass, momentum, and energy, okay? So we're going to look we're not going to cut it into small shell like this, but in this case, we're going to consider it as a whole system. But of course, we're not going to derive an equation for a whole body or whole system, but we're going to consider a small piece out of that represents the whole system, okay? And then, yeah, it will be easier, more straightforward than the shell balance, okay? So first thing first, we need to derive the equation of conservation in terms of transport phenomena, okay? So let's consider a physical quantity of a species in the fluid, okay? So let's say that B, I'll define a new variable, which is capital B, okay? B here is the any physical property. So in this case, physical property that I'm saying can be mass, momentum, or energy, okay? So whatever you're focusing, okay, it can be any one of these three, okay? And small b is the same thing. Any physical property per unit mass, okay? Per unit fluid mass, to be specific. Yeah. We're considering fluid, right? Because in transport phenomena, we are dealing with fluid most of the time, okay? So the total quantity of capital B in an arbitrary control volume V is fixed in the system, okay? So previously, let me write it again. We're going to have four terms, which is in minus out plus generation equal to accumulation, right? We're going to derive and construct a term for each four terms right here into the equation, okay? So right now, let's start with the accumulation term. So accumulation terms for B can be write as a rho B volume V, okay? So let me show you in for this example, okay? If I have a system like this, okay, and of course, in terms of transport phenomena, we don't have to take a whole piece into account, right? We can just consider a small area or small volume, okay? So in this case, if I times with dV, capital V here is the volume, okay? So B here is equal to density times the small b dV. So if I integrate it, okay, it's going to include all of this of the system, okay? So let's check if both sides are actually equal, okay? So density, you know the density, the unit of density, what is it? Kilograms, let's do SI unit, okay? Kilograms per meters cube, okay? What about B, small b? Is the B divided by kilogram because it's the per unit of fluid mass, right? Okay, and dV is here, okay? So the unit for B will be equal to B. Both sides units are equal, right? Okay, so now we have accumulation term, but of course it has to be in terms of with respect with time, okay? So we have to differentiate it, okay? dB by dt. Okay, so of course, on the right hand side, it will be dt rho b dv. All right. Actually, let me show you this first. Okay, can I erase this for a second? On the left-hand side here, you're seeing that I'm using total derivative, right? Let me go back to this page again. You can see here that we have three different types of derivative, right? And what I'm using for the accumulation term is actually the total derivative, okay? In this case, why? Why I'm not using partial derivative or substantial derivative? But in this case, for the accumulation term, I'm using the total derivative. Because it's more general in this case, because B can change with time, and B can also change with the direction in X, Y, Z direction. Okay, so to distribute the total derivative term of B, okay, it can be written as dC by dt integrate of rho B dV plus the X integrate with V. Can you see that? Can you see the last part? Okay. So if I distribute the whole term for total derivative of capital B, it will be in four terms, okay? Similar to what I just showed you in the previous slides, right? Let me know if you can read any part, all right? So if I want to simplify the equation, okay? If I say that the change in our system, the change in the system in terms of x direction, y direction, and z directions is zero. Okay, there is no change in terms of size or geometry of the system. Like for example, this is the system that we're focusing on right now, right? If we're saying that the size here doesn't change with time, so it means that dx by dt, dy by dt, and dz by dt is equal to zero, right? So all three terms right there are equal to zero, okay? Because there is no change in terms of size with time. Or you can say that the volume is constant, okay? The volume of the system that we're focusing on right now is constant. So what we have left is just the first term here, okay? Any questions about this? Yeah. If you what? Oh, if do you want me to write all the Oh, okay. Sure. But there's only one assumption right now. Okay. Sure, sure. So, assumption is that if, oops, just put it right here then, so that in the same page. Assumption that there, is it too small? There's no change in size of the system with time. So in this case, I would say that the volume, the constant volume, sorry. Right? Does it make sense? All right. So now we have one term already. Okay, so we already have accumulation term. So I'm going to color it. Okay, accumulation term, which is this term right here. All right, this makes sense to make it clear. So you can see here now that at the end, eventually, we're going to put this term into this equation. All right. Can I rewrite this actually? The previous one, dB by dt. Okay, is that? Oh, sorry, it's not a big D. It's not a big D. All right, dB by dt, accumulation term here. We can actually put the d by dt derivative in the integrate. Okay, which is this one, because as we just make an assumption that the volume is constant, right? The volume is constant. So derivative d by dt here can be taken in or out of integration. All right. All right. I'm going to highlight it again. Hmm. And you can see here that in the integration, it's with respect with the total volume, right? The total volume of this system that we're looking at right now. Okay, so you can imagine that the rest of three terms here, in, out, and generation, will be with respect with the dV2, same volume, because we're looking at the same system. Okay, all right. Next one, let's take a look at the net input. Okay, I'm saying the net input because in minus out, okay, I'm going to combine it as a net input. Okay, because whatever is coming in minus coming out, it will be the net. Okay, net input, let me say in terms of rate of net input. So the slide that I showed you, the last slide that I showed you in the PowerPoint previously, okay, if you remember the last slide that shows the summary, all the transport is in terms of the flux, right? Okay, with respect to time and area. Okay, so in this case, for the net input, I'm going to use the symbol JB. Okay, and the flux right here is also a vector because when you consider a small piece of your system right here, it can be in any direction. It can be going in or going out of this area, right? So of course it's a vector, okay? So once, when it's a vector, I make a single double line, single line right here too, okay? So if I write the unit for this flux, it will be a B, right? Any physical property with respect to area and time, okay? Which is equal to rho times B times V, velocity, okay? Let's check if both sides are actually equal, okay? The unit of the density is equal to kilograms per meters cube. All right, B is big B divided by kg, okay? And velocity is meter per second, okay? Does the unit of both sides equal? Yes, all right. So we have the rate of net input, okay? Rate of net input equal to JB dot N ds, okay? Because the flux of whatever coming in or out can be in any angle, okay? I'll come back to this again. Hold on. Let me go back to this slide. You remember this picture that I showed you? For example, if we have a vector, for example, velocity right here, right, going out of this area, it can be in any angle. It doesn't have to be in a perpendicular to the area, right? So if you want to incorporate into the equation, you need to dot with the normal vector, okay, right, like this, v dot n, okay. So same thing with the this one, okay, jb dot n, because in this system, if we consider this small area here, the flux can the net input of flux can be going in or going out and in any direction, okay? So we have to dot it with the normal vector, all right? And since we define it as a net input, so it means that the flux is going in, right? It's going in. So we have to put the negative sign in front of this term too, because we already defined this at the beginning that whatever is coming in is going to be negative. Whatever is coming out is going to be positive, okay? So right now we define it as a net input. So we have to add this negative sign too, all right? All right, now we have another term here, okay, which is the net input. So I'm going to make a highlight of this term. All right, we're going to plug this term back into this equation, okay? So right now we only have the generation term left, okay? Okay. Rate of generation, okay? But let's complete this equation first. Since this term is still in terms of ds, right? It's still different to the accumulation term with respect to volume. Yes? The negative sign right here. Okay, if I go back to this slide, you remember this? We define that whatever is coming into the ds, we have it will be the negative sign. Whatever's going out is going to be positive sign, right? But right now we're considering in minus out as a net input. Okay, so it's input is going into the area, so that's why we have to add the negative sign. Okay. Right now we have dV for the accumulation term, okay, as a whole volume. But for the net input, we have the area, right? They are not equal yet. They're not at the same baseline yet. So we need to change this ds into dV, right? So that we can put it into this equation. Okay. So in transport phenomena textbook, the one and only that we use is the Bird Lightfoot Stewart You probably have seen this textbook before, okay? And we're going to use this textbook as a reference for our class too, okay? In the appendix A, if I get it right, there's a theorem called divergence theorem. Divergence. Let's say that the integration of the function f dot normal vector n ds is equal to integration of del dot f d volume, okay? So we're going to apply the divergence theorem into this equation to transform this whole term with respect to area in terms of volume now, okay? So the rate of net input is going to be equal to negative del dot JB dV, all right? And again, I'm going to highlight it. All right. So now we have the same volume now, dV, integration of dV, okay? Yes, function. It can be any vector function. So here, in our case, is the JB, which is the flux. All right, last term, which is the rate of generation, okay? We have rate of accumulation, which is this term, rate of net input, which is this term, and last one. Oops. What is that? Rate of generation, which is equal to RB, okay? It can be anything. So this term here is actually the generation rate per volume, okay? So it's equal to integration of RB dV, okay? And then I'm going to highlight it again in orange, okay? So now we have all the terms. We can plug them all in back into the conservation equation. All right. So that will be minus V del JB dV plus V RB dV equal to V dt rho B dV. All right. This term here is the net input, right? Rate of net input. Let me write it short. This term is generation. This term is accumulation. Okay. And since all the terms here have are in integration, okay, we can take it off. Okay. So it will be, and if I rearrange the equation, it will be rho B plus. Okay. So this is the general form of conservation of physical Okay. So we'll take a break, and after the break, we're going to apply this general form of conservation equation that we just derived right here for mass transport. Okay, so like I said, B here, the capital B here represents mass, momentum, or energy. So this equation is just like a universal equation for mass, momentum, and energy transport. We don't have to do shell balance anymore. We're just going to use this one and only conservation equation that we just derived. Okay, that will be for my part. Okay, yes. The final equation right here. This this one. Oh, so right here, from this general conservation equation, we have net input, generation term, and accumulation term, right? So we just plug all the terms that I highlight, okay? So the accumulation term is right here, right? So I'm plugging back into this term, okay? Rate of net input, which is this term, so I plug it in, okay? And last one is the rate of generation, okay? So it will be written as this one. Okay, so everything is in integration, okay, with the volume, okay, same volume, okay, and since each term is in integration, so we can take it off, okay, so at the end we only have this term. All right, this one. This one I just rewrite it, rearrange the equation. So put this term right here, okay? If I move that one, it will be positive, right? So it will be del dot JB, okay? This one will be changed to negative sign. Is that right? Mm-hmm. So if you can imagine, if we're looking at mass transport, the small b right here, or JB or RB, will be in terms of concentration, okay? Concentration, flux of concentration, right? Okay, so let's take a 10-minute break and we'll come back at 10:30, all right? We're going to apply this equation into the mass transport. So if you have any questions during this time, you can come see me. Okay, so before this, we have derived the general form of conservation equation shown on this screen here, okay? So we're going to start applying this equation into the mass conservation now, or mass transport, all right? Okay. You know that in any system, there could be like a mixture, right? It's not, it might not be a single species in the system. So if we consider a particular species, okay, in terms of mass, so it will be pretty different to other types of equations like energy or momentum. So for mass, if we consider the mass for species I, okay, earlier we know that capital B, big B, is any physical property. It can be mass, momentum, or energy, right? So in this case, B, small b, BI. So I would specify with the species I as well, all right? So that will be, in terms of mass, it will be density, okay? Density I divided by total density, okay? Because small b is equal to big B divided by unit fluid mass, right? So in this case, it will be rho I divided by rho, okay? So rho I defined as the mass I divided by fluid volume, okay? And for rho, which is the total density, okay? So it will be the fluid mass divided by fluid volume, okay? That's it. Then if I go back to this equation, you would see here that we have JB, right? JB is the flux. So in this case, if we are considering the mass of species I, okay? So JB in this case, JBI is equal to, previously we have JB equal to this one, rho B times V, velocity, right? So that will be rho BI, because we're focusing on the species I's, VI. Okay. And if you take a look at this terms here, rho times BI is actually equal to rho I. Is that right? Okay. So that would be VI. Okay. Then we have in this equation, we have RB, right, which is the generation term. So RB in this case will be, I'll use the small r, okay? And if I write the unit for this, it will be the mass of species i's divided by volume per time, okay? So from general form of conservation equation previously, okay, which we're going to substitute all these terms into equations, okay? So for species I, so that will be rho I by rho T plus del dot. Okay. Does that make sense? That is actually it for the mass conservation or mass transport equation. Okay. But to apply this equation into real problems is, it won't be easy. Okay, it won't be easy because if you take a look at this equation, this term right here is actually accumulation term, right? This term right here is the generation term, okay? And the middle term right here is the rate of net input or the flux, right? The flux coming in and out. So if you remember, the two mechanisms of transport phenomena includes two types, right? Convective and molecular transport, right? So this term right here has to include molecular transport and also convective transport. Is that right? So this one, molecular transport, is actually equal to the diffusion, right? Same thing. Is that right? And the convective transport, the other term. So I'm going to distribute this middle term right here into diffusion term and also convection term, so that when we apply this equation into real problems, it will be easier to plug all the terms into the equation. Is that right? All right. So we're going to transform this term into molecular term and convective term. Okay. Okay. Let me start by saying that, for example, if we have a system consisting of two species, species A and B, Okay, species A and B. So if we have a lot of components of A, B, okay, and it's moving at different velocity in any direction randomly like this, okay? So in this case, we're going to have velocity A, which is the average velocity of A, is that right? Velocity of A. And we have velocity B, which is the average velocity of B. And also V, which is the mixture velocity, okay? So if I say that V, let's say V A minus V, what does it mean? It's going to tell you that the species A is faster than the average velocity of the mixture, right? How much A is moving faster than the average mixture velocity, okay? And if I multiply with the rho A, what would it mean? Before this, we don't have rho A, right? It's just telling you how much A is moving faster than the average velocity. But if I multiply with the density of A, of the species A, what does it mean? It's going to tell you in terms of the mass flux now, okay? Like how much A is moving faster than the average velocity in terms of mass, okay? Because we multiply, oops, sorry, we multiply it with density now, okay? And if you want to check with the unit, okay? The unit for this will be kilograms per cubic meter, and velocity is meter square, okay? So the unit at the end will be kilograms, oops, sorry, this is not, is going to be the mass flux. Is that right? This is the unit of mass flux. Kilograms divided by area divided by time. Is that right? Okay. So this whole term right here that I'm pointing right now is actually the mass flux, and it's actually the diffusion flux too. For example, it's a diffusion flux. Let me write it first. Diffusion flux. So if you imagine that if I have like a pipe with the flow of a mixture of water and salt, okay, but they're not fully dissolved, okay. Let's say that the concentration of salt is too saturated, okay. So there will be some particle of salt in the brine, in the salt solution too, okay. So there will be a average velocity of the solution and also the velocity of the particle of salt too, okay? So if they're flowing into this pipe, okay, they're not moving at the same speed. The fluid is going to move this like this speed, but the particles of salt will be moving maybe slower like this, okay? So what's happening is that there will be a diffusion going on from salt into the solution, right? So that is, this term is telling you about, okay? The concentration of salt is higher than that of the water, okay? And it's, so that's why the speed or the velocity of the salt is not equal to the average velocity of the whole solution, okay? So that is that there will be a diffusion flux going on in this case, okay? Excuse me a second. Hmm. All right. And if I define that the small j right here, JA, okay, is a diffusion flux. Okay, JA is a diffusion flux. So let me distribute this term here, rho A VA minus rho A V. Okay, and if I rearrange the equation, okay, it will be rho A VA equal to JA plus rho AV, okay? All right? So here is a diffusion flux, right? Diffusion flux. This is actually the convective flux. And this term right here will be the mass flux. All right? It's like a mass flux right here is going to include diffusion flux and convective flux, which follows by the two mechanisms of transport of mass, right? Molecular transport and convective transport, which is this term and this term, okay? Are you still following? Okay, all right. Just want to check. So if I go back to previous slide earlier, you see this term right here, right? Rho IVI. So it's actually a mass flux, right? That includes molecular or diffusion and also convective term, which is equivalent to this term right here. Okay. So in the previous equation right there, I'm going to substitute these both terms into equation so that there will be two different terms of diffusion and also convective flux. All right. So replace in the previous equation, it will be rho I dt plus J, small j. This is small j now, which is a diffusion flux, all right? Plus del dot rho I V minus Ri equal to 0, okay? And please remind that all this term here is scalar, all right? Any questions? So if I write this one is the accumulation term, right? This one is the generation term, okay? And the two middle terms right there are the rate of net input term, okay? Which includes both molecular term and convective term, okay? This is the diffusion or molecular. This term is the convective term. Why do I need to separate into two terms like this instead of the one term like this equation? It's because when you apply this equation into real problems, like I mentioned, okay, it will be easier for you to substitute into these terms because some of the some of the system, there is no convective term. Okay, there's only diffusion going on, so you can just plug the diffusion going the diffusion term into this equation, okay, or the other way around. But if you apply this equation, you won't know how to plug the term into this equation. For example, if you have only diffusion, how are you going to plug this term, the diffusion term, into this equation, right? That's why we need to separate into two different terms right here, okay? That means that when you solve the equation, you need to understand the problem first, what kind of transport mechanism it has for that system. Is it a diffusion or is it a convection? Okay. If you don't understand or if you cannot apply it correctly, then you will mess up when you plug in into this equation. All right. Okay, this is in terms of the mass form. Okay, you also know that when we talk about the mass conservation, it can be considered as a molar form as well. Is that right? So we're going to convert this equation into molar form too, because most of the cases, the problem is giving you the mass value in terms of concentration in molar form rather than mass form. Okay. Okay. This is the equation of continuity of species I. Okay. So to convert it into molar form, of course, you just have to divide with the molecular weight, right? To this equation, okay? So molar form, you just divide it by the molecular weight of species I. So that will be concentration, dc. So now I change the velocity into the v star so that it's it shows the difference in terms of the one in mass form and the other one in molar form is different. Okay, and same thing with the generation term. The mass form I use small r, and for molar form I use big R. Okay. Or this term, I can rewrite it. This is the diffusion term, right? This diffusion term I can use as a big J star, okay? Big J star, Ji star. It's the molar diffusion flux. Any questions? So it depends on the problems, okay? If it's in the mass form, you just use the top equation, the equation on the top, all right? But if it's the information in the problems giving you in the molar form, just use the bottom one. And these two equations are for species I in the mixture, okay? But if we consider the overall mass in the system, okay? So for overall mass, we just have to sum all the species in the equation, right? So I'm going to use the sigma sign, okay? Del dot sigma ji plus all right. So if you consider overall mass, you just need to sum it all up in each term, okay? Let's take a look at each term here. Let's start with the first term. What would be the sigma rho I? Sigma rho I. Let me move to the next page, okay? Sigma rho I. ทันไหม? Okay, sorry. It's okay. No. Take your time. Take your time. No. Don't waste your time after class. You just need to finish this in class. Any questions during this time? Yes. The molar form, the symbol is what? Oh, I can't see, sorry. Molar form, yeah.
Yes, it is a symbol.
Oh, this is, no, it's multiply. Multiply with 1 over molecular weight. So you just divide all this term with the molecular weight. This is multiply. Yeah. Mm-hmm. All right. Can I move on now? All right. So let's start with the first term here. We have sigma rho I. What does it mean, sigma rho I? So let's say if I have rho I is equal to mass fraction of I times total density. Is that right? Okay. And if I have another species which is J, rho J is equal to mass fraction of J times total density. Okay. So sigma rho I, okay, it will be rho I plus rho J. So that will be equal to omega I plus omega J times rho. Okay, so the summation of the mass fraction, how much is it? 1, right? So it will be equal to rho. So sigma rho I is equal to rho. All right. All right, next term is sigma Ji, which is this one, okay? Let's find out how much it is, okay? Sigma Ji, so same thing, it's going to be let's say Ja plus Jb, okay? That will be rho A times Va minus V plus rho B VB minus V. Okay? You still remember this? Where does it come from? This is the diffusion flux, right? Diffusion flux comes from, sorry, I'll come back. From this equation. You remember this? The one that I'm pointing at right now. Okay? Okay? So let's distribute all the term. Okay? So I'm going to group them up here. Rho A, VA plus rho B, VB. Okay, and then rho AV plus rho BV. Please check for me too, okay? I can be wrong sometimes. All right. Rho A. Rho A is actually equal to rho omega A times A. Is that right? Same thing with rho B. Rho omega B VB. Okay? Same thing with the last term. If I take out the V, which is the common term, okay, it will be rho A, rho B times V. Is that right? Okay. So now we have rho as a common term for the first term. Okay. So it will be rho A VA plus omega B VB. Okay. What is this term? What is this term? And what is this term? It's actually equal to average velocity. Is that right? And the second term right there, rho A plus rho B, how much is it? It's just a rho, right? It's just a rho. So how much is the sigma Ji? 0, okay? So if I go back to this equation, okay, this term is 0, okay? I'll give you guys a few seconds to write this down. We have 2 more terms left. We'll be done soon. Yes. 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 But maybe after Sunday, because we have Sunday class too, and that class is after us. Okay. So please wait for a bit. Any questions? Yeah. Oh no. All right. Good. All right. Next is what else? Del dot sigma rho IV. Okay. Sigma rho IV. This term right here, since rho I, we already derived, right? That is equal to rho. So this term right here is actually del dot rho V. Is that right? Okay. And what about the last term, sigma Ri? Sigma Ri, the last term right here. What would it be? It's actually equal to 0. Because whatever's generated or whatever's anything generated, it's going to be consumed, right? So mass is conserved. And if we sigma, right, sum them all up, so anything generated or consumed is going to be equal to 0. All right? So neglect this term. So we have only 2 terms left from this overall mass equation. All right? All right. So let's rewrite this equation. So at the end, we will get d rho by dt plus del dot rho v equal to 0. That's it. Okay. And that is the overall mass equation, or we say that this equation is actually equation of continuity. You've heard this name before, right? Equation of continuity. Last but not least, it's not completely done yet. All right. Let's focus on this term right here. Okay. Let's take a look at this term. We can actually transform it into another form, actually. So if we recall this term, del dot phi A. Oh, it's coming back again from last week. if you still have your note lecture from last week, this term is actually equal to del phi dot A plus del phi del dot A. I haven't shown you this step yet, but please review it yourself, okay? But we already gone through these three terms already last time, okay? So from the equation of continuity, we can rewrite that d rho by dt is going to be del rho dot v, sorry, del rho dot v plus equal to 0, okay? It's the same thing, right? So you can take rho equivalent to phi because both are scalar, okay? And velocity and vector A are both vector, right? So they are equivalent. So you can rewrite that equation, continuation like that, okay? So this term right here, we can actually switch, okay? So we can write this as a v dot del rho, okay? Do you see anything familiar? Anything familiar to you? D rho by dt plus v dot del rho. Right. Let me go back to the previous slides. Do you see anything here? Does it look similar? dc by dt plus v dot del c. It's actually substantial derivative, right? So right here is actually d rho by dt plus rho del dot v equal to 0. Okay. This is also equation of continuity, just transforming the equation. Okay. All right, last but not least, for mass conservation, okay? If we can assume that the fluid property does not change, in this case, it's the density. Do you still remember the fluid being incompressible, incompressible or compressible? Do you know what the incompressible fluid means? What is it? Yeah, the volume doesn't change, right? It means that the density doesn't change either, okay? So that is the definition of the incompressible fluid. Incompressible fluid means that it cannot be compressed, okay? So the volume is fixed. That means that the density is also constant, okay? It doesn't change with time or pressure, okay? So if the system, the fluid in your system is incompressible, okay, it means that the density is constant, meaning that this term, this whole term here, this term here, d rho by dt is going to be 0. Is that right? And that means that rho del dot v will be equal to 0 too, okay? And rho will be equal to 0, okay? So in terms of incompressible fluid, incompressible. The continuity equation will be transformed only this term, del dot V equal to 0, okay? This is very, very important, okay? Can be used only for incompressible fluid, all right? That means that the density doesn't change with anything at all, doesn't change with time, doesn't change with temperature or pressure, okay? And most of the incompressible fluids is just, for example, liquids, okay? And maybe a few examples of gas too, but mostly liquids, all right? So if the fluid in your system is not an incompressible fluid or it's being compressed, right? Is a compressible fluid, you have to come back to use this equation instead, okay? So it will be more complicated, okay? But if it's an incompressible fluid, you can just apply this equation. So next time I will show you the full equation corresponding to different coordination systems, okay? It's actually in the appendix of the textbook, okay? I will post it on my course view as well, okay? Because we're going to apply those equations into our exercises next time, all right? I think we still have time left, so let's move on to the equation of mass conservation of species I for a little bit because so you can understand how to use and apply this equation, this equation right here a little bit better, okay? As you can see here, in this equation, which is in the mass form and also in the molar form as well, okay? You can see here that there's a diffusion term and also a convective term, okay? Here, oops, sorry. You might wonder, let me see, let me use this. How are you going to apply the diffusion term into the equation? Okay, sorry. Let me go to the next slide. Let's just focus in the binary system, okay? Meaning that there's only two components in your system, okay? If you want to apply the diffusion term into the equation, okay? We are going to use the fixed law equation, JA, which is equal to rho diffusivity del omega A. All right. Omega is actually the mass fraction. All right. And if you divide it by molecular weight, same thing. The JA here, which is the diffusion term in molar form, will be equal to total concentration times diffusivity or diffusion coefficient times del XA. All right. So yes, the sign or huh? Or D in big D. Yeah. Is it diffusivity or diffusion coefficient? Yeah, like A diffuse in B, for example. So in this case, we have to make an assumption that the total concentration and the total densities are constant too, okay? Rho, Z are constant. So if I come back to this equation, let me copy this. Okay, So if I want to plug in the diffusion term, which is this term right here, okay, diffusion term, okay, I'm going to apply the fixed law, which is this equation, okay, plug it into this equation, okay, right here. So let me say that if the system has only diffusion, there is no convective term, okay? For example, so if I neglect the convective term right here, we're going to consider only the diffusion term or molecular transport, all right? So what we have is that we're just going to have the rho d rho I by dt and apply the fixed law, which is the rho d a b del square omega A, oh, omega I, sorry, minus Ri equal to 0, okay? So now you can apply this equation and plug all the terms into the equation and solve it. Because if you use this equation, okay, how are you going to plug the actual numbers into this term, right? You have to apply the fixed law. So in fixed law here, you can apply the mass fraction. Of course, it's the known value. Also the constant diffusion coefficient and also the total density. Okay, so now you can solve this equation. So this is in mass form, right? Mass form. So if it's in molar form, it will look similar. So it will be rho Ci by dt minus total concentration del square Ci minus Ri equal to 0. Okay. Don't forget that we have del dot Ji right here. Okay. Del dot Ji. So if you have del dot with the fixed law term right there, it will be del square. Okay. Any questions about this? All right, last topic for the mass transport for today. Okay, can I move on to the next one? Not yet. Right. So in general, for solving the mass conservation equation, there actually, in general, there are three cases that we normally see in problems. Okay, so I'm going to show you three different cases. So these are all in binary systems. Okay, binary system. Let's say there are two components, which is the A and B in the system, which is of course binary system in rectangular coordinates to simplify it. All right. If we have case number one where we have dilute A. Okay, dilute A, meaning that the let's consider a molar form. Okay, the molar fraction of A is reaching 0. Okay. I think I will move this part to the next week. Yeah, because it will be quite a lot as far as I've seen. And I will incorporate some exercises along too, so that you can have a understanding about, different cases like dilute A or other two cases. Okay, so maybe I should stop for now and move this part to next week. Okay, so that the content will be continuous. Okay, I don't want it to, yeah, as far as I've seen, yeah. I think let's move on to next week. So next week, we're going to continue this part and then practice a few exercises with the mass conservation equation. All right. Any questions about this? Any part at all? No? All right. So you have about 45 minutes early free time. All right. So if no other questions, then see you next week. All right.